Have you ever faced a problem where you need to find the OR of two sets in a matrix, but the solution seems out of reach? It can be quite a challenge, right? If that's you, then you're in the right place. Today, we're diving into a more efficient algorithm to tackle this problem. I completely understand how frustrating it can be when you're dealing with large matrices and trying to optimize your approach. You're not alone in this struggle. Many have faced the same issue, especially when the naive method just doesn't cut it. Here's the specific situation we're looking at. One user recently asked, how can I efficiently find the number of pairs of rows in a matrix where their OR equals all ones? They mentioned trying a naive method with a time complexity of O of n squared times m, but it just wasn't efficient enough. Sound familiar? Let's explore this together. So what makes this problem tricky? The challenge lies in the size of the matrix, which can be up to 3,000 rows and columns. We need a solution that avoids the brute force approach and finds a way to optimize the search for those pairs. And don't go anywhere. I've got a powerful technique to share at the end that will help you solve this problem efficiently and impress your peers. To find the number of pairs of rows whose OR results in a row of all ones, the user should first understand the properties of the OR operation. Specifically, if two rows OR together to produce a row of all ones, then every column in those rows must contain at least one one. Next, the user should create a bit mask for each row. This bit mask will represent the columns where the row has ones. The user can achieve this by iterating through each row and setting the corresponding bits in an integer. After generating the bit masks, the user should count how many times each bit mask appears. This can be done using a hash map. The user will then need to check pairs of these bit masks to see if their OR equals the target bit mask, which is all ones. Finally, the user should calculate the number of valid pairs. For each unique pair of bit masks that meet the criteria, the user can multiply their counts to get the total number of valid row pairs. Did you know? The concept of OR operations in computer science is similar to how we combine ingredients in a recipe. Just like you can't make a cake without flour and sugar, you can't achieve the desired OR without the right combinations of bits. Now let's look at the answers provided by other users. The user presents several alternative approaches to efficiently find the OR of two sets of rows in a matrix. First, they mention a trivial solution that involves checking all combinations of rows, which runs in O n squared times m. They then suggest a constant speedup by packing bits into words, which can improve performance on 64-bit machines. Next, they propose a heuristic method that sorts rows by their Hamming weight, allowing comparisons only between low and high weight rows, potentially speeding up the process. Another idea involves grouping rows based on a column with low Hamming weight, reducing the number of combinations to check. Finally, they note that while it's challenging to beat the ON squared worst-case scenario, focusing on the number of valid pairs can lead to better performance. That wraps up that answer. Let's move on to another one. An alternative approach to finding the OR of two sets involves breaking down the problem into smaller subproblems. First, we categorize the rows into groups based on their starting bits. This allows us to focus on three main combinations, reducing the complexity of the problem. Next, the user suggests selecting the column that minimizes the size of the subproblems. This can be done by calculating the number of zeros in each column beforehand. Additionally, they recommend using Hamming weight pruning to eliminate rows that won't contribute to the OR result. Finally, sorting the rows can speed up the splitting process using a bisection algorithm. The overall complexity of this method is estimated to be around O n squared log n times m, with potential for better average case performance. Now, let's shift our focus to a different response. An alternative approach to finding the OR of two sets involves viewing the problem as an exact cover problem. Each row in the matrix represents a set of column indices where the value is 1. The The goal is to find rows that form a disjoint partition of all column indices. When only two rows are involved, they are binary opposites, which is what we need. However, more complex combinations can also exist, such as with 3 rows. This exact cover problem is NP-complete, and a well-known solution is algorithm X, developed by Donald Knuth. That's the end of that answer. Let's see another perspective. An alternative approach to finding the OR of 2 sets involves a more efficient ON times M algorithm. First, for each column, we create a mapping of row indices that contain a 1. Then, for each row, we determine which rows can complete it by intersecting the sets from the previous step. Finally, we count these completing rows. For example, in a matrix with 3 rows, we identify which rows can fill in the zeros for each row. The result shows that there are 2 pairs of rows that can achieve the desired OR. Let's take a look at an answer from another user. An alternative algorithm suggests leveraging the presence of zeros in the rows. The idea is that if 2 rows share a 0 in the same column, they cannot form a valid pair. The algorithm starts by creating 2 sets, one for all row indexes and another empty set. It then iterates through the rows from bottom to top, checking for zeros. If a 0 is found, it checks other rows in the active set for matching zeros, moving incompatible rows to a separate set. Finally, it counts the valid pairs and updates the sets accordingly. Here's the pro tip I promised. Always think about how you can represent your data in a way that makes operations faster. Using binary representations can save you a lot of time and effort. And there you have it. With these techniques, you should be able to efficiently find the OR of 2 sets in a matrix. Remember, optimizing your approach is key. If you found this helpful, hit the subscribe button for more tips, and don't miss our next video where we tackle even more complex algorithms.